Welcome back to the Lee channel with more physics. In this video, we're going to look at components of a vector. In class, hopefully you know the difference between a vector and a scalar. A vector has both magnitude and direction, scalar only has magnitude. In this video, we will learn how to name a vector in a 2D space, and knowing how to take a vector and breaking it down into its horizontal and vertical components. So what is this vector and components all about? When we look at motion or anything to do with space, we're not only limited to a single line. Most of the motion happens in a 2D plane, if not a 3D plane. But for this course, we're only going to be looking at 2D space. So usually we have a sort of x and y axes, and when we draw a certain vector, the vector may fall into a vector is going to have some bit of its motion in the x direction, some of its motion going to be in the y direction. To describe this vector, we are going to look at how much it moves horizontally and how much it moves vertically. So that's what this component thing is about. To name a vector, the name begins with the magnitude and then the direction. The 2D plane, or the x and y coordinate, can be in either the north, south, east, west direction. So imagine you're walking on the field, on the football field, and you can either go left, right, center of the field. So you can either go north, you can go, say, east, you can go west, and you can go south. So that's one 2D plane. Another 2D plane in which you can fit your x and y coordinate is the up and down plane. So up and down is, imagine I throw a football upwards. It has some sort of upward component and it has some sort of a sideways component. And this can be either in the north-south, or this up and down can be in the east and west. I ran out of space. Oh, there it is. So there's many 2D planes that you can imagine, but we're only working with 2D motion, not 3D. When you describe a vector that is in this form, so kind of looking at up and down and left and right, we start with a magnitude. So I have here an example, 44 meters per second, which is a velocity. We'll learn that later. At a particular angle, we'll say 45 degrees, and this can be above or below what we call the horizontal. Let's say above. I'm just using this example over here. So what that looks like is, imagine this is the ground. And imagine you have a person. And imagine this person is going to throw a football. And let's say this person's going to throw it at some particular angle. And this angle, we call this 40, let's say this is the 45 degrees referred to in an example. And when we say above from the horizontal, it means imagine there is a horizontal line that's parallel with the ground. And 45 degrees above it is, imagine you take an arrow and rotate it at this pivot up from the horizontal like this. Okay, so that is the vector rotating upwards from that horizontal. So that is the vector. And along with the magnitude, 44 meters per second, the throwing speed, which I don't think is humanly achievable, or maybe it is. Anyways, this kind of is what that horizontal looks like. On the other hand, if we said 44 meters per second at 45 degrees below the horizontal, it would look like this instead. So this would be 45 degrees going below the horizontal. Imagine taking a minute hand or an hour hand of a clock and waiting for it to tick downwards in a clockwise direction. So going down like this. So this is 44 meters per second at 45 degrees below the horizontal. This is working with a 2D plane where imagine the y-axis is being up and then the x-axis being horizontally parallel with the ground in a certain direction. Then you have a 2D plane of motion happening kind of parallel with the ground. So what that looks like would be more of this scenario. So imagining going across the field, down the field, left and right and center, etc. So we're dealing with north, south, east, west direction, And in this particular case, the language becomes a little bit confusing. So let's break this down. We usually start with the magnitude, always. I will take example 2 as an example. Let's say I have a displacement of 1,500 kilometers at 33 degrees. So this is an angle. And then I have 2 reference locations, directions. I have one being north, one in the one in one axis of east. This one is in the other axis. So what does this all mean? If I want to take the example here to draw this out, here is what it would look like. So imagine my football field. I am going north of the football field, for example, and a little bit of east. So I'm going to generally draw my arrow in this direction. I'm going to just draw one arbitrarily. I know that this guy is 1,500 kilometers. And where does the north of east come from? There's a few ways how I tackle how to memorize the nomenclature here, the language. One way of thinking of it is from a linguistics perspective, which means think of it as it's 33 degrees north of the east, which means north is a descriptor while east is the actual direction. East being the actual direction, what do I mean by the actual? I'm meaning this takes importance over north, is north of the east. So east goes first. When I draw this, I start at my base where my object starts. Imagine at the base of my arrow. I draw the east. This is east. And then I draw north second because north is describing north of the east. This is second. So then I draw this arrow showing that this arrow goes north. So why is it important to make this triangle? The reason why we want to make this triangle is because we want to specify this particular angle. This angle is 33 degrees, which is in the vector itself. Not this one, but this guy down here. You can also think of it, well, when I read this, this is the opposite direction, the opposite of what I would think. What I mean by opposite is, you would, instead of going north first, you would go east first from the starting position and then go north. The other way how I like to think of it as a little gimmick is thinking of it as a tan function of tan theta. Remember, tan theta is opposite over adjacent. So imagine this is my angle 33 degrees. Opposite to this would be north of the east. So north is first and east is second from tan theta. This is just a little gimmick that I use to remember this way of naming vectors. So when I wrote up here, I wrote the second arrow, meaning that this one goes second after the first arrow that leaves the starting position over here. Let's do another example. If you want to, you can pause the video, try this first, and then look at if your response matches with mine. What I would do here first is I am going to draw the general shape of my arrow as my vector. Southwest kind of looks like this. At this point, I don't care how angled it is. I just want to get my vector down. This is about 420 newtons. Now, to describe whether this 68 degrees means this angle or this angle relative to my coordinate axes, x and y, I need to look at the language, south of west. If you take a look at south of west, we look at the second word, which is west, the second direction being west, south describing the west, west goes first from the starting position. So I draw my arrow west first, then south, which is my second one. So then I draw this going south. If you thought of it from a tan, if you use a tan theta as a little gimmick, then you probably would have done this. You probably would have done, well, south is going to be my opposite from this position over here. Opposite to that is south, and west is the adjacent relative to this point. This is west. So doing it backwards. Whichever way works for you. Just remember that south and west, the order of which the words are presented, would be the opposite way of how you would draw the vectors from the starting position from your blue one, the original vector itself, or the resultant. The angle as a result would be this guy over here. Below are a few cases where you would name the vectors. Let's do one together first, and then I'll let you try the second one. Example number 4, we have 15 meters, and then you have 22 degrees downwards, and then we have a little compass that shows us north, south, east, west, sort of like a coordinate system of x and y. To name this vector, we have to be careful of our coordinates first. We have going in this direction is east, going upwards is north. To name this vector, we first write down the magnitude. Magnitude would be 15 meters per second. The next thing to say is an angle at 22 degrees. If we have to be very careful where the 22 degrees is. 22 degrees is this guy over here. To get this 22 degrees, we have to first start at the base of our original vector. To draw the arrows, we want to first start at the base of the arrow and then find what vectors we need to draw this kind of a triangle shape going around the angle and reaching all the way at the end. We first go east and then we go south. Normally you would say west and then south, but using the nomenclature, it's backwards, it's flipped. If south was second and east was first, we would say this is south of east, because east comes first and south comes second. South is describing the east, or if you think it from a tan theta as a gimmick way to remember, this is opposite and then adjacent. Or if you think, oh, it goes east and then south, instead it will be the opposite, south of east. Let's do another example. Example number 5. Also using this north, south, east, west as a coordinate system. To name this vector, we first start off with the magnitude, which is 0.94 Newton second. This we will talk about later as what it means. At 41 degrees. First we talk about the angle, and we look at how can we draw a triangle to encapsulate this degree. We start at the base of our vector, we trace out, okay, first we go down south, and then we go west. So drawing this one out, south is first, west is second. But when we name it, it's the opposite. So this is 41 degrees west of south. The nomenclature, the naming is a little weird. Hopefully you have a little bit sense of it, how it is. Now you can ask yourself, is there another way to name these vectors? Think about it. What if I chose to go the other direction? And then going down this way. I do have a different angle, but I also know that the combined angle or degrees added together from here all the way to here is 90 degrees, which means this guy over here would be 49 degrees. If I have to name this vector using this new triangle, you take a look, well, this time I went west first, and then I went south. So naming it, it would be 0.94 Newton second at, this time is 49 degrees, but this would be going south of west. So notice as you flip the angles, using the other angle, the complementary angle, you also flip the directionality as well. Check for the inquiry question. The next part, we're going to look at how to break vectors into their components. This might deserve a new video. So I'm going to stop here. I'm going to ask you to watch part 2 of vector components. See you in part 2.